Welcome to part 2 of the scatter plots and correlation video. What you're going to learn is about a variable called the correlation coefficient. The variable r is called the correlation coefficient, and it is used to illustrate the correlation between two sets of data. Here is a scatter plot where the r value is equal to 0. What does the correlation look like when the r value is equal to 0? Hopefully you said it doesn't look like there's any correlation. So when the correlation coefficient, or r, is equal to 0, there is no correlation between the two variables. So your scatter plot just looks like a smattering of points, and you're not able to tell whether there is an upward trend or a downward trend. Now, as the correlation coefficient approaches 1, so as this gets closer to 1, I want you to take a look at what's happening to the data. So there's a correlation coefficient of 0.13, there's 0.26, there's 0.38, 0.51. What's happening as you approach 1? So hopefully you answered. As your correlation coefficient approaches 1, your points tend towards a positive correlation and they get stronger. So the closer you get to 1, the stronger the correlation is going to be. So your line of best fit would be increasing to the right, and the points would be getting closer and closer to the line of best fit. So what does the data look like when r is equal to 1? So if we change r to be equal to 1, what you end up getting is a perfect correlation. In a perfect correlation, every single point is on the line of best fit. So if r is exactly equal to positive 1, you have a positive correlation with every point lying on the line of best fit. Now let's take a look when r approaches negative 1. So we'll put it back to 0. And now what happens when the r approaches negative 1? Hopefully you'll see that the trend is now becoming negative, and the closer you get to negative 1, the stronger the correlation. So the line would be going in a downward trend, and your points would be getting closer to the line of best fit. Now if r was equal to 0.8 and positive, and if r was equal to negative 0.8 and negative, these two scatter plots would have the same strength, just different directions. So even though numerically 0.8 is higher than negative 0.8, it's the magnitude of the number that tells you how strong the correlation is, and it's the sign of the number which tells you which direction. And I'm sure you can guess now what it would look like if your r value is exactly negative 1. You guessed it. It is a perfect negative correlation with your trend line decreasing and every point lying on the line of best fit. So your correlation coefficient ranges from negative 1 up to positive 1, with negative 1 being perfectly negative and positive 1 being perfectly positive and 0 being no correlation at all. So the bigger the magnitude of the number, the stronger the correlation, and the sign tells you which direction the correlation is in. So the correlation coefficient measures the strength and the direction of a linear relationship. So it has to be linear for you to use the R value. The linear correlation coefficient is sometimes referred to the Pearson product moment correlation coefficient in honor of its developer, Carl Pearson. This is the formula for calculating R, and you guessed it, we are going to use that formula to calculate R on the next piece of paper. Calculating the R is about the same kind of work as calculating the standard deviation. There's a lot of steps, but the math itself is quite easy. N is the number of pairs of data, and the X, of course, are the values of the domain, which is the first column or row of your table, and Y is the values of the range, which is the second column or row of your table. So this illustration is just a guideline, not a rule. So 0 would be no correlation, -1 would be a perfect negative correlation, +1 would be a perfect positive correlation. Now, an R value anywhere from 0 to about 0.33 or -0.33 would be considered a weak correlation. If you go between 0.33 to about 0.67 or -0.67, it's in the moderate range. And then anything up to 1 or -1 would be considered a strong correlation. So 0.8 would be a high or a strong positive correlation. -0.8 would be a high or strong negative correlation. -0.3 would be a low or a weak, and 0.3 would be a low or a weak. And you can use different descriptive words. So if you had 0.7, you might say it's a moderately strong correlation, whereas if you had 0.9, you could say it's a very strong correlation. 0.1 would be very weak, 0.2 might be somewhat weak, 0.3 might be moderately weak. So you can use those descriptor words to help you describe where within that range your correlation coefficient is. Now, one problem that arises in interpreting R values is that their relative magnitudes are not proportional. That is to say, a correlation coefficient of 0.8 cannot be said to be accounting for twice as much go-togetherness as a coefficient of 0.4. That means 0.8 is not twice as strong as 0.4. It's difficult to interpret and understand correlation coefficients, especially relative to each other. The number itself doesn't exactly have a meaning. So the 0.8 doesn't mean that 80% of the points are on the line of best fit. It doesn't work that way. All you can say is 0.8 would be a relatively strong correlation, and it's stronger than a 0.3. So it's kind of like the standard deviation. The number itself doesn't have so much of a meaning. It's just more useful when you're comparing it to other things. So we're going to end the second part to the video now. This was a bit of a shorter one, but in the third part to this video, what we're going to do is show you how to calculate the correlation coefficient. So please ensure that you watch part 3 of the video. Thank you.